Welcome, Algebra 1 students, to Unit 4.1, Arithmetic Sequences. You are hearing the voice of Mr. May, and I will be walking you through this particular unit. As always, please make sure that you have your guided notes available. We will be completing them as we proceed through this particular lesson. Make sure you use that pause button to work out the examples on your own before listening to my explanations, and always use that rewind button to review concepts that you may need a little additional time working with. And without further ado, let's begin. Our learning targets for this particular lesson, we have 4 of them, each dealing with sequences. Learning target 4.1a, I can write an explicit arithmetic sequence formula to model a situation. Learning target number 4.1b, I can write a recursive arithmetic sequence formula to model a situation. Learning target 4.1c, I can write a recursive process that describes the relationships between two quantities. And learning target 4.1d, I can translate between recursive and explicit formulas. Just to point out a couple of important points. The first being that we are going to be using sequences to model situations. Secondly, we have 2 different types of arithmetic sequences, one being an explicit arithmetic sequence, the other being recursive. We're working with arithmetic sequences in this particular unit, meaning that we're going to be dealing with addition and subtraction. And lastly, we are going to learn the relationship between recursive and explicit formulas because we can translate between the two. We can turn a recursive formula into an explicit formula and vice versa. So our definitions. The first is a mathematical pattern. And a pattern is a repeated design or recurring sequence. Pattern recognition is a very important skill. As a human being in general, we apply it not only to mathematical processes, but we apply it to everyday situations in life. If you can become proficient, or I guess using a more school-based term, distinguished in recognizing patterns, you become a very valuable employee, but I would say human being, in that you can recognize situations and be able to make great decisions within a specific context. Pattern recognition is a great skill to practice and build on in general, but in this case we're going to use it in a specific mathematical context. And that mathematical context is going to be working with sequences. And so a sequence is built of sequence terms. So terms in a sequence. Now we've talked about terms in general in previous units, specifically Unit 2.1, where we talked about terms of an expression. And in this case, we're going to have terms of a sequence, and the application of it is going to be a number that is located in a specific position within a sequence. Now, a sequence has a different meaning, or a sequence term has a little bit different meaning than a term located in an expression. A sequence term is actually going to be, yes, it's going to be a number, which does qualify as a term within an expression, but when we talk about a sequence term, we're talking about that number and its position. So it might be the 25th term in the sequence. It might be the 5th term. It might be the 100th term in a sequence. And just to make sure that we're fully understanding what a sequence is, we talked about a pattern, and you might see a sequence of numbers. So for example, the sequence of even numbers would be 2, 4, 6, 8, 10, 12, and so on and so forth. That is a sequence of numbers. In this case, the sequence happens to be all the even numbers. And if I were talking about a sequence term, I might choose a specific one of these, and I might choose the 10, which is a term in and of itself when we talk about an expression. But in this sequence, it is that's my first term, second term, third term, fourth term. It is the fifth term in the sequence of even numbers that begins, in this case, begins with 2, my initial term of 2. So that is what the meaning of a sequence term is in this context. And then lastly, we have recursive. Recursive is repeatedly using a procedure or rule to obtain successive results. And the way that you could kind of think about it is recurring. We're looking at a recurring process, something that happens over and over again, and we use the same values or previous values to obtain the next value. And so in the case of our sequence of even numbers, in that case, we have a recurring procedure or rule, and the recurring procedure or rule in this case is when we move from the first to second to third to fourth to fifth term, what we are doing is we are using the same procedure over and over again. And that procedure in this case is adding 2. That is the recurring procedure, or the recurring rule is to add 2 to get to the next term in the sequence. It recurs over and over again. And so we're going to repeatedly use a recurring rule, and that rule is going to be specific to the sequence. In this case, our specific rule is adding 2 that is going to occur over and over again. So we're going to determine what each rule is that is specific to that sequence, and then we're going to be able to write a generalized rule so that we can determine any term in a sequence. And so let's move forward. We're going to get a little bit more specific as we really narrow down the difference between a recursive and an explicit formula. So a recursive sequence is a sequence that has each term calculated, and the important thought here is in order using the previous term. Okay? And I must know the previous term in order to calculate the current term that I'm on. And so in this case, let's go back to our example of even numbers. So if my even numbers are 2, 4, 6, 8, 10, so on and so forth, if I want to find a specific term in a recursive sequence, let's say I want to find the 6th term. I want to determine it. So if I want to know what the 6th term is, what I would need to know, because I don't have any generalized rule in this case. We've already discussed what we're doing. We're actually adding 2, but because I've not been given a general rule that I can just calculate any 30th term, what I would need to do is I would need to say, okay, 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 8, or 6 plus 2 is 8, 8 plus 2 is 10. So now I have 1, here's my first, second, third, fourth, fifth. Well, to get my 6th term, I'm going to add 2, and I know that my 6th term is going to be 12. Now that was relatively straightforward because I just needed to know the next term of the sequence that was given. However, what if I were to ask you, well, what's the 25th term? Well, immediately you couldn't tell me what that 25th term was or is, because there is not a generalized rule to calculate that 25th term. So the process in this case will be relatively lengthy. You would have to add 2 again to get 14, and add another 2 to get 16, and so on and so forth until I got to the 25th term. And as you can see, right now I'm only at the 8th term, so I would need to do this 17 more times to find that 25th term. So a recursive sequence, as you start wanting to find terms, sequence terms that are further out, you can see that it can become pretty laborious in calculating that by hand. Which leads us to our next type of sequence, which is an explicit sequence. And I'm going to move this just a little bit. So an explicit sequence allows us to calculate any term without having to know, without knowing the previous term. So if we look at the case of our even numbers, once again, our sequence of even numbers, 2, 4, 6, 8, 10, we calculated the 12, so on. With an explicit sequence, what we can do is calculate that 25th term without going through the entire process of adding another 2 to get 14, adding another 2 to get 16, and so on and so forth until we get to that 25th term. An explicit sequence will allow us to immediately substitute in a value of that 25th term, substitute in the value of the term that we want to calculate, and our result will be the value of that specific term. So the difference between recursive again and explicit is recursive. You have to go through the long process of calculating each term in order to find a specific term number, sequence term number. And an explicit sequence allows us to just skip the entire calculation of everything in order and go to the exact term value that we want to know. Next we have an arithmetic sequence. Now an arithmetic sequence is one in which a fixed number, so it's the same number. When we say fixed number, kind of think of that as same. So we have the same number added. This is a very important concept. Added to each previous term. Okay? So the mathematical operation has to do with addition. And remember, we add negative numbers. So even though it may look like we are subtracting in some cases, we are adding the negative. That is the terminology that we need to use. Now, how are you going to remember that an arithmetic sequence adds one number to the next? Well, arithmetic begins with the word or the letter A, and added also begins with the letter A. And so when you see the terminology arithmetic sequence, know that you are going to add either a positive number or add the negative number to each previous term. And so let's look at an example. In this case, the fixed number, and I'll highlight it in green just to make the connection to the fixed number in the definition. The fixed number that we're going to add, again, we have the add, which makes this an arithmetic sequence. So we're going to add the fixed number 3 to each term, and we're going to begin with the first term of 1. And so our first term, or our initial term, you will also see this going forward. First, you will see that as called initial term as well. So our first term or initial term is 1. And we're going to add the same fixed number each time. So in this case, we're going to add 3. 1 plus 3 is 4. 4 plus 3 is 7. 7 plus 3 is 10. 10 plus 3 is 13, and so on and so forth. The same number is added to each term. Now, we're given a specific number of terms all the way out here to term number or value of 40, which looks like it's term number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we are given 14 terms in this sequence. If I wanted to calculate the 100th term, you can see that it might be a little bit lengthy process to calculate another 86 terms to figure out what that 100th term is. So in this particular case, I only have what would be called a recursive sequence because I don't yet have a generalized way to calculate that exact 100th term without going through the entire calculation in order of the sequence of adding 3 to each previous term. So we have a recursive sequence in this particular case. Now, let's do another example. Write an arithmetic sequence beginning with the first term. So again, our initial term. Let's call this our, and let's highlight in this color because we've got an initial term, which we also call first. So this first or initial term of 2. So I know I'm going to begin with 2, and I'm going to add 5 to each previous term. So what I'm going to do is I'm going to add 5, and I'm going to get 7. I'm going to add 5 and have 12. Add 5, 17. Add 5, 22. And so on and so forth until I can get whatever number of sequence terms that I desire. That might be in this case 1 to 5, or I could calculate theoretically to infinity the number of terms that I want to have in my sequence. Once again, this is a recursive sequence because I have to specifically add 5 to each of the previous terms to calculate the next term. So a little bit of terminology. In the previous examples, we called the fixed number that we were adding we just called it the fixed number. We didn't give it any specific definition or terminology in and of itself. However, what you're going to see going forward is that fixed number is called the common difference, and that is what we are adding to each previous term. So in the previous examples, our fixed number or our common difference were 3 and 5. And I'm going to return to the previous slide. So our fixed number or our common difference was 3 in this example, and the common difference was 5 in this example. So going forward, you might see adding a common difference of 3, or you might see adding a common difference of 5. So that is the terminology of that fixed number. So going forward, we're going to use common difference. So we're going to use common difference when we are wanting to write sequence. Now, if we want to find what that common difference is given a sequence of numbers, we can calculate that common difference by subtracting the first term from the second term. Now, what does that look like? Well, we have an example down here. And when I look at my first term is 4. Or my second term is 4. My first term is 1. And I need to subtract the first term from the second term. So when I subtract, I will have 4 minus 1, which is 3. So my common difference should be adding 3. So let's check to make sure that that's accurate. Well, what is 4 plus 3? Well, it's 7. 7 plus 3 is 10. So our common difference in this sequence would be adding 3 or plus 3. Let's find the common difference in this sequence. Well, once again, we can take the second term. Let me keep this uniform. So we can take my second term and we can subtract the first term. Well, my second term is minus 3. I'm going to subtract a negative 7. Remember, when we subtract a negative, we're actually adding, so what we really have is negative 3 plus 7, which means that our common difference is plus 4 in this case. So let's see if this is accurate. Well, negative 7 plus 4, that is negative 3. Negative 3 plus 4 is 1. 1 plus 4 is 5. 5 plus 4 is 9. That is correct. So our common difference is adding 4 to the previous term to calculate the next term. Once again, please make sure that you realize when you add, when you subtract a negative, you are actually going to add. Okay, do not forget that. This brings us to an arithmetic sequence rule. So once we have the ability to find the initial term and we have the ability to calculate the common difference, we can now be able to translate from a recursive sequence to an explicit sequence. And so we don't have to go through the lengthy process of calculating each term in order. We can now just choose an exact term that we want to know, that 100th term, for example, and calculate it directly. And an arithmetic sequence rule is what allows us to translate from that recursive rule to an explicit rule. Okay, so now we're going to be able to write explicit sequences so that we can quickly determine a specific sequence term. Once again, we're going to be working with arithmetic sequences. And so the generalized form of an arithmetic sequence rule is a to the n equals a plus n minus 1 times d. That is the generalized rule. All of our arithmetic sequence rules will be written in this form, in this generalized form. Now, each one of these terms, once again, we have terms, and let's highlight our individual terms. So we have each of these are considered terms in our rule. Let's not use this, and I think, there we go. Okay, so each of those is a term, and each one holds a specific meaning. Now, a to the n. This a to the n is our function notation for the rule. Now, function notation we'll talk about a little bit more specifically in a future unit in Unit 4, or a section in Unit 4. We'll talk about that a little bit more specifically, but the function notation for the rule basically says the value of a specific term n. Okay, so n, the n that we find here, and let me go ahead and actually highlight these so you can see that they're going to be the same n. The n that we find there is this same n, and it's the explicit term number being calculated. So for example, if I want to find the 100th term, then n would be the value of 100. And what it would look like is a to the, I want to find the 100th term, and that will equal the rest of my arithmetic sequence rule. So this just tells me I'm looking for the 100th term, is what that tells me. And now we're going to use the parts of that to find the rest. So our a, lowercase a, is the first term in the sequence, our initial term. And the way that you can easily remember this is lowercase a, or a in general, is the first letter in the alphabet. And so if the first letter in the alphabet is a, I'm looking or needing to know or going to use this as the first term in the sequence. N, once again, is the explicit term number I'm looking for. It's that specific term number. It might be the 100th term. It might be the 1000th term. It might be the 10th term. It could be any number that we choose, and we can skip, again, that lengthy process of calculating each term in order to find that 100th term, for example. And then lastly, we have the common difference. The common difference is that fixed number that we are adding to our sequence in order to calculate that next term. Okay, so each of these has a specific meaning that is going to allow us to write a generalized rule so that we can calculate any value or specific term value in the sequence. So let's put this in practice. So we're given right now a recursive sequence. The reason it's a recursive sequence is I do not have the ability at the moment to find the 100th term without calculating the next, let's say I have 1, 2, 3, 4, 5, 6, 7, 8, 9 terms, so the next 91 terms. I would have to calculate 91 terms to find that 100th term. So what I can do is I can write an arithmetic sequence rule, and that will allow me to calculate that 100th term. So once again, let's just write our generalized form. It's a to the n equals lowercase a plus m minus 1 times d. And remember, each one of these has a specific meaning. So our generalized rule, we're not going to find a specific term number yet. We're going to substitute that term number for n once we determine the exact term that we want to calculate. So right now we're going to write the general rule. So the general rule we know is going to be a sub n equals, now a, remember a, the first letter of the alphabet. Being the first letter of the alphabet, I know that that is giving me the clue that that is going to be the value of the first term in the sequence, which in this case is 5, plus, once again, we're not worried about n because we just want to write the general rule. We don't want to calculate a specific term number yet. So I'm going to leave the n minus 1. Well, that leaves d. D, remember, is the common difference. So d is my common difference, and it makes sense, right? Because d and difference. And the common difference is the fixed value being added to each previous term to calculate the current term. And the way that we find the common difference is to take the second term, which in this case is 7, subtract the first term, which in this case is 5, and we get a value of 2. And if we want to check ourselves, 5 plus 2 is 7. 7 plus 2 is 9, 9 plus 2 is 11, 11 plus 2 is 13. Looks like we have the correct value for our common difference. And so now I can substitute my common difference into the arithmetic sequence rule, and now I have a general arithmetic sequence rule that represents or models this specific sequence. Now in this case, if I want to find that 100th term, because now I have an explicit rule, okay, remember these are explicit rules, okay, explicit rule, it's an explicit arithmetic sequence rule that allows me to now calculate an exact term. Well, we've talked about that 100th term quite a bit, and so if I want to have n equal to 100, or the 100th term, what I would do is I would substitute 100 for n. Now again, as a reminder, this first n, that is not a times 100. That is not what that means. That does not mean a times 100. All that means is that I'm looking for the value of term number 100. That's all that means. Please do not attempt to multiply a times 100 in this case. That is not the meaning of it. It's just saying I'm looking for the value of the 100th term. I can now substitute, so we have 5 plus 100 minus 1 times 2. And I can evaluate it at this point. You can substitute all of this into the calculator, and if you substitute it into the calculator, this is the only portion that you need to substitute into your calculator. Okay? And what it equals, the value that it equals, is is this value here. Okay? So it's a of 100. It's the 100th term. So I'm going to calculate this. I'm probably going to do it by hand here. So a 100 is 5 plus 100 minus 1 is 99 times 2. And so a of 100 equals 5 plus 99 times 2, I believe, is 198. And so moving over here, just have a little bit extra room. The 100th term value is 203. And so if I were to calculate this by hand the long way, starting here and saying plus 2, I get 23, plus 2, I get 25, and so on and so forth. When I got to the 100th term, that value would be 203. So writing an explicit arithmetic sequence rule, and in this case my general rule, this is my general rule. By writing this general rule, it allows me to skip the process of plus 2, plus 2, plus 2, plus 2, plus 2, until I get to the 100th term. It allows me to skip that process and go directly to that 100th term, which in this case, the value of it is 203. And that is an example that highlights learning target 4.1a and 4.1b. Let's do one more example. Example number 2, learning target number 4.1a and 4.1b is being highlighted. And once again, we are going to write an arithmetic sequence rule for the following sequence. So we need to write down our generalized form, a sub n, or a to the n, equals a plus n minus 1 times d. So we have our explicit arithmetic sequence rule formula, and we have to determine our specific values that we need to substitute in. Well, we realize that a to the n, or a of n, is our value of whatever term number we're looking for. A, first letter of the alphabet, meaning our first term in the sequence. So I'm going to substitute 15 for A, plus, once again, we're going to leave the n because we're not looking for a specific term number. We're looking for a generalized formula. So n minus 1, and the d is our common difference. So I have to calculate or determine the common difference. So in this case, to find the common difference, I'm going to take the second term, which is 10, and I'm going to subtract the first term, which is 15. And so my common difference is going to be -5. Now, you may be thinking, wait a minute. I thought an arithmetic sequence has to be adding the same fixed number. Well, that is true. But remember, when we talk about addition in algebra, we think of subtraction as adding the negative. Okay? So even though you may think, oh, I'm subtracting 5 in each of these cases, Remember, we must think in Algebra 1, we must think that instead of subtracting 5, we're adding a negative 5. So our common difference can be a negative number. We just have to recall that we are adding the negative. And so when I substitute my negative 5 in for D, it's really good practice to put it in parentheses because, just let me show you, I'm going to write the end part here. If you were to simply write it this way, technically what you're doing is this says subtract 5. And we're not wanting to subtract 5. We're wanting to multiply by negative 5. So especially with negative common differences, make sure that you substitute them using parentheses. Otherwise, the order of operations suddenly becomes subtraction and not multiplication. Excuse me. And so that is my generalized explicit arithmetic sequence rule. Now, before we find a specific term number, you may recall that with a recursive arithmetic sequence, to find the 100th term, what you have to do is you would have to subtract 5 and get negative 25, subtract another negative 5, get negative 30, and so on and so forth until you get to that 100th term out here somewhere and figure out what the value is. And so that is a recursive arithmetic sequence. And so what we wrote was an explicit explicit arithmetic sequence rule. And that's an explicit rule. Now, if I wanted to write a recursive rule, this shows what's happening recursively. Excuse me. What I'm going to need to do is I'm going to need to write it in a bit of a different format. And the format that it's normally written in is we use this set notation bracket, and we give a couple of pieces of information. The first piece of information that we give is what the value of a sub 1. Now this little notation here, that's called a subscript. Okay, subscript means below. Okay, think submarine, below water. Well, subscript means just written a little bit below the term. And so what this is saying is a sub 1, and I guess technically we need to put the 1 there. And so that a sub 1 is going to be our first term. And so in this case, we're given the first term of 15. Okay? So we have to be given the first term because otherwise we're not going to know where to start the rule, the sequence, right? And so the next thing that we're going to need to do is we're going to have to say, okay, so a to the n plus 1, okay, so a to the n plus 1 means that the next term in the sequence, okay? So this is going to tell us that this is how we calculate the next term, okay? So that tells us the next term is equal to the current term that we're on and then what we're going to do to that current term to calculate that next term. So, excuse me, in this case, what we're going to do is we're going to subtract 5. Okay? And that is our common difference. So let's think about it. Or we're going to add a negative 5. So let's think about it. If I want to know the second term, okay? The second term. Well, in order to calculate the second term, I have to use the first term, right? So this is how I'm going to erase this here so I can write this below. And let's use a different color. So if I want to know the second term, okay? So what it would look like is this. Okay? Now what does this tell me? Well, we know that a sub 1, this means my first term. Okay? So this little subscript here is telling me my term number, right? That's telling me which term number I'm on. So that's telling me I'm on the first term. So you can see what happens when I rewrite this a sub 1 plus 1, 1 plus 1 being 2. So when I rewrite this 1 plus 1 as a sub 2, you can see that that's saying term 2. So now I have a sub 2, or term number 2, is equal to a sub 1. Well, what did we say that a sub 1 equaled? Well, a sub 1 is 15. It's my first term. It's my initial term. And so I'm going to take that 15 and substitute it in, minus 5, which is the operation that I'm performing to that term. And so I get the value of my second term, a sub 2, is equal to 10. And if you notice, 10 is my second term. And so what we have written here is a recursive rule. So now I have the explicit rule. I have the explicit rule. Oh, not what I needed. I have the explicit rule, and then I also have the, here's my explicit rule, and I also have a recursive rule. And each of these rules are interchangeable. You can translate from one rule to the other. Now remember, the recursive rule must calculate in order, okay? What's that mean? Well, it means that I can't find the 100th term with this recursive rule. I have to know the 99th term in order to find the 100th term. You have to know the term before. I can't skip to the next one. So we just calculated the second term, right? And we found the value of 10. Well, if I wanted to calculate the value of the third term, well, here's what I would have to do. I'd have to say a to the 2 plus 1, which will give me 3. I have to say a sub 2 minus 5. And so 2 plus 1, a to the third, which is my third term, is equal to, well, we just calculated the value of this second term, correct? We calculated that as the 10. So I'm going to substitute the value of 10, subtract 5. The value of my third term is 5. And so now if I want to calculate the fourth term, I would have to do all of that process once again, substituting in all the values to calculate the fourth, and then the fifth, and so on and so forth. That is just a formalized rule for what more than likely you're doing in your head as you calculate each term in sequence. On the other hand, if I want to find the value of we've calculated out to the third term, so let's do that as well. So if I want to find the value of the third term, remember, substitute the value of 3 for n. All I need to do, and actually it might be better practice, you might see what I'm doing, if I show where I'm substituting that 3. Okay, now I've written the explicit rule for specifically finding the third term. Remember, that is the term number I'm looking for. Okay, I'm looking for the third term. And so when I calculate the value of the third term, I end up with 15 plus 3 minus 1 is 2 times negative 5. And so I have a sub n is equal to 15 plus 2 times negative 5 is negative 10. 15 minus 10 is 5, which is the value, this 5 is the value of my third term. And just to show you that we could use the recursive rule, we have a 2 plus 1, have to use the value of the second term, minus 5. So I end up with a sub 3. We said the value of the second term was 10. Minus 5. And so we have a sub 3 is equal to 5. It is the same, wrong thing. It is the same value. And actually, to use best practice, let's go ahead and change this so that it is also a 3. So we have the ability with an arithmetic sequence rule to calculate any term number recursively, which is the long way, and we also have the ability to calculate it explicitly, meaning that we can skip to the exact term that we want to find, whether it be, in this case, the third term or the 1,000th term. It does not matter, using the arithmetic sequence rule that we wrote, whether it be a recursive rule or the generalized form of an explicit rule. So that is example 2, highlighting learning targets 4.1a and 4.1b. As always, if you have any questions or concerns, go back, rewatch this, make sure you fully understand the concept. And if you still have some questions, please find one of the math teachers. We are more than happy to help you clarify any questions that you might have. As always, have a great afternoon or evening, and we look forward to seeing you in class.